In this module, we will explain the importance of high motor efficiency. We will also take a trip inside an electric motor to find out what we mean by efficiency and explain the losses that occur within the motor that contribute to its efficiency rating. The world is facing a serious energy challenge. Demand for electricity will grow faster than for any other form of final energy. Pressures to reduce energy consumption and lower carbon dioxide emissions come from everywhere. The simplest way to address this challenge is to seize the opportunities for energy reduction that come from using energy more efficiently. Over 40% of generated electricity is consumed by industry, and 2/3 of that energy is used by electric motors. By increasing efficiency using more efficient motors, it would be possible to realize huge savings in both energy and carbon dioxide emissions. This has prompted governments to introduce MEPS, Minimum Energy Performance Standards, setting mandatory minimum efficiency levels for electric motors. So what is motor efficiency? Efficiency is simply the ratio of output power to input power and presented as a percentage. Let's take a standard motor with a 75 kilowatt output. Achieving this output requires a power input of 80.9 kilowatts. Using our formula, we get an efficiency of 92.7%. This also means that the power losses amount to 5.9 kilowatts. So where do these losses come from, and how can they be minimized to increase the motor's efficiency? We will try to explain that in a simplified way. The no-load losses shown here are almost constant regardless of the motor load. Stator iron losses are present due to the energy required to magnetize the core material and includes losses due to the creation of eddy currents that flow in the core. They can be decreased by using better and thinner electromagnetic steel and lengthening the iron core. Friction losses are present due to the friction in bearings and shaft seals and can be reduced by correct dimensioning and selection of bearings. Windage losses are caused by air resistance in the fans and can be reduced by optimized fan and airflow design. After the no-load losses, we have the load losses, and here there are 3 types. Stator winding losses, or I²R losses, are present due to the current flow through the resistance of stator winding. They can be reduced by optimizing stator slot design with the windings tightly packed to ensure a good slot fill-in ratio, together with an optimized iron core to maximize the strength of the magnetic field. Rotor losses. The rotor also suffers I²R losses caused by the rotor currents, as well as iron losses caused by the magnetic flux interacting with the rotor core. They can be reduced by increasing the size of conductive bars and end rings to produce lower resistance. Additional load losses, or stray load losses, are present due to the leakage flux caused by variations in the windings, mechanical imperfections in the air gap, and irregularities in the air gap flux density. They can be reduced by improving slot geometry and minimizing deviation in the air gap. Unfortunately, losses are an inevitable part of running a motor, and since they directly affect the efficiency, manufacturers of premium motors do their very best to reduce them. By using higher quality materials, cutting-edge motor designs and manufacturing in high-precision automated factories, losses are kept to a minimum. This means that with every successive generation of motor design, efficiency gets improved and contributes to solving part of the global energy challenge. In the next module, we will look at the cost of ownership and provide a few tips on how this can be reduced.